Welcome to section 17.2 on nuclear stability. You can see I came inside. It was too cold for me out there. I got some Florida blood in me now, so hopefully you did those section review questions and you can be nice and ready for 17.2 on nuclear stability. Here's my wife. So why do atoms hold together in the first place? Good question. If we understood that completely, I think that you would probably win the Nobel Prize, because we really don't understand how atoms hold together. You have this massive concentrated nuclear particle called the nucleus in the middle of an atom, and it's held together even though it's completely positive with some neutral charges. It doesn't make sense. Why does it do that? Positives repel each other. We know that. And surrounding this nucleus is a buzz of electrons in orbitals. And anyways, we know how it works. We just don't really know too much why it works. Besides, we have this idea called the strong nuclear force. Real creative in its naming, right? It's a force which acts on protons and neutrons to keep them together. It's not real understood. But I believe it's part of God's design. I put 2 verses down there. Fortunately, I have my Bible right here. And Colossians 1:17 says, "He is before all things, and by him all things consist." And so that's my understanding of it. He's holding it together through what we call the strong nuclear force, even though it's not really understood that well. Here's a radioactive decay series. Things decay. We talked about that just a little bit with carbon-14. It's too large. It falls apart. If you have really large things like uranium-238, it's going to spontaneously split apart. And it's going to become something smaller. And you can see here how U becomes TH, which becomes Pa, which becomes uranium again, back to a smaller form of TH, to radium and radon and polonium and lead and then bismuth. And you can see how each time it's getting smaller, it's shedding layers of its nucleus to become a smaller atom. So this is unlike us. And talking about weight again, it'd be very similar to this. Let's say I weigh 130 pounds. That's 6 foot tall. 130 pounds is not good. And so I randomly, because my body's unstable, I shed height. So now I'm 130 pounds, but I'm only 5'6". Well, that 5'6", 130 pounds is healthy. It'd be kind of like that, and it's just kind of strange to think about it, but that's how atoms do what they need to do if they are too large for their own nucleus. Now we have this problem. It's called a nuclear mass defect, and for a little while we were able to measure using very precise and unique ways the mass of a proton, a neutron, and an electron. Now, protons and neutrons weigh a whole lot, considering their size. Electrons weigh very little. I think your textbook mentions that if you had a 50-pound dumbbell, protons and neutrons would make up 49.99 pounds of it. That's quite a lot. It means electrons weigh very little, or have a mass, I should say, of very little. But if you add all the protons, neutrons, electrons together, for instance in oxygen-16, you get 16.13 atomic mass units, or U. However, if we take the mass of an oxygen, oxygen-16, we get only 15.99. Where'd the mass go? Did it break the law of the conservation of mass that we've been talking about all semester? It did not. And Einstein demonstrated this with what he called the nuclear mass defect, explaining how energy can be related to mass as well as the speed of light. he said that a tiny bit of energy can be converted to mass, and a tiny bit of mass can be converted to energy. So actually, when we weigh those things and it comes up with 16.13 U, he's saying that a small portion of that is actually energy that is, and this energy actually has mass, and it's recordable. And in this case, it's 0.14, which is the difference between 16.13 and 15.99. And this 0.14 is a very valid mass measurement, but when oxygen 16 is together, it is recorded as energy instead of mass. And that's because of his very famous formula, E equals mc squared. That's one use of that formula, by the way. There are multiple uses. Binding energy, the amount of energy released when a nucleus is formed. And we'll have a chart on the next page to demonstrate that. Small atoms fuse to become larger atoms. So that's how our sun works. So you have hydrogens from the sun. These hydrogens fuse together under massive energy and become helium. And this helium releases energy. Nuclear fission works the opposite way. If you have uranium, uranium can spontaneously split apart. It splits apart into all sorts of different things. One of its most famous things uranium splits apart into is iodine. And we're going to talk about why later, but that's called nuclear fission, when large atoms split into medium-sized atoms. Iodine is a very recordable atom. It's not huge. So anyways, that's nuclear fission, nuclear fusion. You can see how the binding energy goes up and it peaks at iron, Fe. So this is the energy of formation. So if you form iron, iron formation is actually the thing that causes the most energy to be released, strangely enough. But these atoms, they will interact with fusion. They will fuse to become larger things. These atoms will go through fission, break apart to become smaller things. And so iron, anything to the left of iron, typically fuses in a nuclear reaction. Anything to the right of iron typically goes through fission. So that is just some helpful hints there. You can see in nuclear fission, breaking apart, you have uranium-235, a stable isotope of uranium, encounters one neutron, gets too large, uranium-236 too large, breaks apart into barium and krypton, and 3 neutrons. And so these two isotopes are stable, and these neutrons go out and they can potentially cause some damage, but they're also released with a massive amount of energy. And this is how an average nuclear reactor works, where you have a stable isotope of uranium that receives one neutron. It breaks apart into some predictable isotope of 2 different atoms, as well as some other neutrons, to keep stirring the uranium that's already there, and it produces energy. And we harvest that energy. Nuclear fusion, you can see how the hydrogen form together to produce a hydrogen that is a little bit heavier as a neutron. There's a specific name for it. I think it's, do you remember? Chemistry 101? Deuterium or something? Anyway, you can look it up if you'd like. In fact, the first person to email me what you call a hydrogen with one neutron We'll get a bonus point on the test. How about that? We'll see who really watches these videos. And I think it begins with a D. And then this one down here begins with a hydrogen with 2 neutrons. I think begins with a T. I don't remember. But anyway, that goes back to college chemistry. And anyway, these hydrogen form together to make helium. This is my point. And helium, watch out. Oh, my wife gets the bonus point. Was I close in how I said it? Well, I was right. Ha! No, well then we'll make it 3, or no, we'll make it the one with 2 neutrons, because I was right, because I remember everything. So all right, and that's the end of the lecture. So that's the end of 17.2. Make sure you do your section reviews on page 292. All right, have a good evening, or whenever you're watching this, afternoon, morning, and hopefully we'll get to see you guys in school eventually.